The next thing we're going to be talking about within the kinematics unit is velocity and speed. I know we've talked a little bit about velocity so far when we were talking about acceleration, how acceleration was the rate of change of the velocity. But we didn't really do a full definition of it, nor did we talk about the difference between velocity and speed. So in everyday language, velocity and speed really have the same meaning and are often used interchangeably. That's not true within the world of physics. Velocity and speed are not the same. They have two very specific meanings, and they're two different meanings in the world of physics. So let's start with speed. Speed is simply a measure of how fast or the rate that something is moving. 45 miles per hour, for example. Velocity, on the other hand, is how fast and in what direction something is moving. And that really is the key word there, direction. So if instead of saying an object is moving at 45 miles per hour, we say it's moving at 45 miles per hour southwest, we're now talking about a velocity as opposed to a speed. Okay, so speed is simply how fast it's moving. The way you can remember this is when you're driving in your car and you look down to see how fast you're going, you look at the speedometer. Okay, the speedometer is a device that tells you your speed. The speedometer does not indicate your direction. If it did indicate your direction, it would no longer be a speedometer, it would be a velocitometer or something along those lines. All right, velocity, on the other hand, does include a direction. Connecting this back some to what we talked about before, speed is going to be a scalar because there's no direction involved. Velocity, on the other hand, is a vector. This is a little bit of a unique situation in physics. We don't normally have two different words where they mean very, very similar things, and one's a vector and one's a scalar. That's not going to be the case, but here is one example. Both quantities, though, really measure rate. Okay, both measure how fast something's going. Like we said, the only difference is that direction piece. So both are measured in units of distance over time, meters per second, miles per hour, whatever. The next two things we need to distinguish between are distance and displacement. So distance, which I'm sure you're probably familiar with, is how far something travels. Okay, displacement is slightly different. It's the change in position of an object, including the direction. Now, you might be thinking, well, isn't that the same? What's the difference between the change in position and how far something goes? The way I always think about it is distance is how far you went, okay, and displacement is how far you are from where you started. All right, so really, it's a straight line measurement back to where you started. In some cases, they will be the same, but that's not always going to be true, and we'll actually look at an example on the next page. I do want to make one quick point, though. Once again, we have this weird distinction where one quantity is a scalar, one is a vector, but they mean very, very similar things. I promise this is the last time it's going to happen this year, but in this case, distance is a scalar because it's purely a measure of how far you go. The direction that you travel in, the path that you take does not matter. Displacement, on the other hand, is a vector because direction does matter. Let's take a look at an example here to help show the difference between distance and displacement. For those of you that run track, you know that when you take one lap around that track, you've run 400 meters, essentially a quarter of a mile. So your distance, how far you travel when you do that, is a quarter of a mile. Think for a second, though, about what your displacement is. You start at one part of the track, run one entire complete lap back to where you started. So what would your displacement be? Keep it in mind that displacement is how far you are from where you started. Your displacement is actually nothing, okay, because you start at one part of the track and you finish exactly where you started, which I always think is the silly thing about running track. Most of the races, you end up exactly where you started. What's the point? All that effort to get back to where you started. Your distance, though, would still be a quarter of a mile because that's how far you actually traveled. Another example here, looking at this curved path, okay, the distance would be the length of this line here. If we were to stretch it out into a straight line, the length of that would be the distance. The displacement, on the other hand, is going to be this direct line from where we started to where we finished. All right, displacement is how far we are from where we started. Distance, on the other hand, is how far we actually traveled. Keep in mind, too, that displacement does have a direction, so if we wanted to get technical, we'd have to assign a direction to this line from where we started to where we finished. One last question before we move on to the next bit. Think for a second about when displacement and distance are equal. There is one case when they will be the same, and that is when we have a straight line. In the case of a straight line, however far we travel, that is how far we are from where we started. So for those of you going back to track for a second, they've run the 100 meter. Your distance is 100 meters. Because you're running in a straight line, your displacement is also 100 meters. One last distinction we have to make here, and then we're going to start putting all this together, and that is the distinction between average and instantaneous. Average is always taken over a period of time. For example, maybe you're driving on a 2-hour trip from here to Harrisburg, and your average speed is 55 miles during that period of time. All right, over that entire course of 2 hours, your average speed was 55 miles per hour. However, maybe on the way there, for example, at 5:18, your speed was 43 miles per hour. That would be your instantaneous speed, your speed at one moment in time. Your average and your instantaneous are not always going to be the same because, right, if you're driving from here to Harrisburg, maybe for a while you're going 65 miles per hour, and then there's construction. You have to slow down to 40 miles per hour, and then you have to go to the bathroom, so you stop at a rest stop, and you're not moving at all. So the average speed is over a period of time, but the actual speed at any given instant, the instantaneous speeds during that period of time, may vary. There is a time when the average will always equal the instantaneous, and that is when we're traveling at a constant speed. If you're traveling from one place to another at a constant speed of 60 miles per hour because you have it on cruise control, that's your average speed for that period of time, and it's also your instantaneous speed at any instant during that period of time. So we're going to start putting some of these things together. The first thing we're going to put together is looking at the difference then between instantaneous speed and instantaneous velocity. So instantaneous speed would be how fast an object is going at a given time, at a given instant. Instantaneous velocity would be how fast and in what direction. And we see there the key distinction yet again because velocity includes a direction. So how fast and in what direction an object is moving. Going back to the idea of magnitude for a second, we could say that the instantaneous speed is simply the magnitude of the instantaneous velocity. If you remember when we were talking about magnitude before, we said that when we were talking about vectors, and we use that word magnitude, it means simply the number without the direction. So if we take instantaneous velocity and look at the magnitude of that, that's simply going to be how fast the object is moving, ignoring the directional piece. And that means that it's really just the instantaneous speed. I've said this before, this isn't a common thing in physics, but we happen to have it for this one special case. Let's take a look now at average speed and average velocity. We just talked about how the instantaneous speed is simply the magnitude of the instantaneous velocity. Well, that is not the case when we're talking about average speed and average velocity. Okay? Average velocity, the magnitude of average velocity is not the average speed. There's actually a very, very specific meaning for average speed and for average velocity in physics. And it comes down to these two formulas here. The average velocity is defined as the displacement over the time. So how far an object is from where it started in a given period of time divided by that period of time. The average speed, on the other hand, is the distance divided by the time. So we need to bring in those two ideas of distance and displacement that we just talked about. Just a quick note here on units. The standard units for displacement or distance are both the meters. That's the standard SI unit. Do keep in mind, though, that distance and displacement have different meanings. The standard units for average speed and for average velocity both are going to be meters per second, and our standard unit for time is seconds. One other thing to take notice of here is that average velocity is a vector, and average velocity uses displacement to calculate it. Displacement is also a vector. That's not a coincidence. They go together. Average speed, on the other hand, which is a scalar, uses distance, which is also a scalar when we're calculating it. So here we have a quick summary of what we were just talking about, looking at the difference between average and instantaneous and velocity and speed. So as we said before, if we're thinking about instantaneous, the instantaneous velocity is the speed and direction an object is moving at a specific time, whereas the instantaneous speed is simply how fast an object is moving at that given time without the direction. When we're thinking about average velocity and average speed, we have these two very specific formulas that allow us to calculate it. Average velocity is simply the displacement over the time, whereas average speed is simply the distance over the time. Okay. As we move forward, this one here is going to be the most important. We'll mainly be talking about instantaneous velocity. However, it is important to know the distinction and to talk briefly about the other quantities that we can use to measure how fast something's going, really. One final note, I just want to address the misconception, and I'm sure this will come up and we'll continue talking about this throughout the year. But this formula I just told you is the formula for average velocity. And it's very useful if you're trying to find the average velocity. However, I found in the past that a lot of people will try and use this anytime they're trying to calculate a velocity. And you need to be careful. Unless the problem or the question or whatever you're trying to find is asking for the average velocity specifically, okay, this formula is not really going to be useful for you. And we'll talk about new ones. We'll talk about other formulas that will be useful. But this formula is not going to be useful for you for calculating anything other than the average velocity. All right, so let's go ahead and start applying some of this average speed, average velocity stuff. So we start with this conceptual question here where we have Steve and Usain racing down a straight track. So when the race begins, here we have Steve. Steve immediately starts running towards the finish line, okay, and ends up at the finish line here. Usain, on the other hand, the race starts. Usain waits there for 2 seconds. And then begins running towards the finish line. And the race ultimately ends in a tie. So the first question we have is, who had the greater average velocity during this period of time? So this is really just a conceptual question meant to apply some of the concepts, but I think it's important that we start by drawing upon the equation here, even though we're not actually going to do math with it, and thinking about what really affects the average velocity of an object. And so the average velocity is really just affected by the displacement and by the time. Okay, so if we think about those two quantities, let's first think who is the greater displacement. Well, the displacement of Steve is going to be from the start line to the finish line. The displacement of Usain is also going to be from the start line to the finish line. So they end up having the exact same displacement. Let's think about the time piece now. Obviously, Usain sits there for 2 seconds before moving. However, if we think about the total time, their total time is the same. And so both their displacement and their time are the same, which means that ultimately their average velocity is going to be the same. Same displacement, same time. All right, for question B, we now want to think about who had the greater instantaneous velocity, and that's really the key word here. So we're really just thinking about this moment right at the very end when they're crossing the finish line. And there's one other important thing to consider with this one is it does tell us in the problem that both run at a constant speed. So once they start running, both people are moving at a constant speed. So if we think about this race, Steve, all right, is going to obviously get out to the early lead because Steve's going to be running for 2 whole seconds before Usain even starts, which means that ultimately Usain is going to have to run faster for that period of time while he actually is running in order to cover that same distance, the length of the race, in 2 seconds less than Steve, if we're only thinking about the period of time when he's running. So that ultimately means that Usain is going to have a greater instantaneous velocity at the finish line because Usain is going to have to catch up to Steve right here so that they finish at the same time. For this next one, we have Katie and Stephanie riding around a circular track on go-karts. They both start at the same position, which we're going to say is right here. After 20 seconds, Katie is going to complete 1 full lap around the track here, all the way around, while Stephanie has only completed a halfway lap around the track. So that's where Stephanie ends up at a time of 20 seconds. And so the question is going to be who is the greater average speed and who is the greater average velocity. Let's start with the first one. Thinking about average speed, we know that average speed is going to be given by the equation distance over time, d over t. They both have the same time here of 20 seconds. That doesn't really matter. So the question really is who travels a greater distance? That, of course, is going to be Katie. because Katie manages to go all the way around the track. That's a greater distance than Stephanie, who only goes halfway around the track. Thinking about the average velocity piece, that equation is slightly different. The key difference for average velocity is that we're thinking about displacement over time rather than distance over time. And so when we're thinking about displacement over time, all right, we think about the displacement of each one. Katie is going to have a displacement here of 0 because Katie ends up in the exact same spot that she started in, whereas Stephanie has some non-zero displacement. It's actually equivalent to the diameter of the circle. So therefore, Stephanie actually is going to have the greater average velocity because Katie ends up where she started and therefore has an average velocity of 0.